Chapter 3, How Data is Transported Over Networks. Well, that's a pretty wide-ranging title, isn't it? How data is transported? Well, maybe. What we're actually going to be looking at in this chapter is a number of things. We're going to continue our discussion about the protocols that exist at the different layers of our TCP/IP model. Last week, we introduced IP addresses and MAC addresses down here in layers 2 and 3. This week, we're going to be looking a bit more at the transport layer, and then specifically, how do we go between these layers, right? In the second half of this lecture, and it's actually a two-parter, we're going to start looking at network equipment, specifically the router, because that lives right here at layer 3. So when we introduced the TCP/IP model, we talked about the concept of encapsulation, which means how when data is introduced up here at the top at the application layer and gets put through the stack all the way down to the hardware layer where it gets belted off across the wire, this data entity, if you will, gets encapsulated or put into an envelope. There's a metaphor. Put into an envelope for the layer that it's in. So let's say we're sitting up here, because remember, human beings, we're not inside the TCP/IP model, we're above it, likewise with our apps. So if I'm sitting there on my web browser and I want to go to Yahoo, and I type in yahoo.com in my URL bar and hit enter, well, that message gets passed into the stack, right? www.yahoo.com. It hits here in the application layer. Well, what application am I using if I'm using a web browser? Probably HTTP or HTTPS. So right here, it's going to get wrapped with information, header and tail information, header and footer information from HTTP. It could be things like formatting, it could be encryption, whatever. Then it gets handed down the stack to the next layer. At the transport layer, is it reliable or unreliable, TCP or UDP? More on that here shortly. But that information gets added to it. The envelope from the application layer gets put inside another envelope from the transport layer. Gets handed back down to layer 3. The transport layer envelope goes inside an envelope that contains the Internet Protocol information. Right? We're going to look at one of those at a packet here shortly, and we're going to see some of the stuff that's written on the front of that envelope. Then it goes to the layer 2, the network interface layer, and there our MAC address information gets written to it. So you can see as I start from the top, I start with a basic message, a payload if you will, and it just gets put inside these other containers as it goes down. A container inside a container inside a container. It's like a Russian Matryoshka doll. One of those stacking dolls. That's exactly what's going on here. So by the time the data heads off across the wire to its destination, it's fully encapsulated. When it lands at its destination, at the hardware layer, and starts working its way up, that's when we have de-encapsulation, right? Network interface layer, layer 2 on the receiving end, opens up the layer 2 envelope, removes the layer 3 envelope and hands it up to layer 3. Layer 3 does the same, hands it to layer 4. Layer 4 then hands it to layer 5, and then that application protocol on the distance end hands the final message over to the recipient, who again is up here somewhere, right? This whole thing is called encapsulation, and it looks exactly like this. Payload into a segment, header gets added to it. That segment goes into a packet, more header information, that packet gets added to a frame, more header and trailer information, and then de-encapsulated on the reverse end. Every single piece of network transmission we do goes through this. Every time you click like on a Facebook page, every time a banner ad pops up on your web browser, this is what's going on. Let's take a closer look here at layer 4, because we keep talking about this. We keep talking about we keep talking about how this reliable versus unreliable thing. Well, I have two protocols that live at layer 4. Right here. Right, so we got TCP or UDP. The whole purpose of layer 4 is to determine, is this going to be reliable or unreliable communication? Meaning, am I getting a delivery confirmation? What is a delivery confirmation? What that means is, if I send something to the post office, I get that little postcard glued to the back of it. When it arrives at the destination, the receiving post office peels that off and sends it back to me. When I get it, I know that my letter has reached its destination. That's TCP. That's what Transmission Control Protocol does. Now, this is considered a connection-oriented protocol, meaning there's communication happening both ways. You can think of connection like a phone call, right? Your phone rings, you pick it up, hit the little phone button to connect, and you're talking. Well, that is a connection. Contrast that to, let's say, like a text message. That's not really a connection. You're sending it off into the ether and hoping that it gets there. Now, I know on modern smartphones it'll tell you if somebody read the message or not. But with that being the case, if that's not there, you don't know if they received the text, read it, or whatever. Don't know, don't care. So which is better? Why would I want delivery confirmation? Well, what it does is it keeps my segments, my data, from getting mangled on the network. It does these things called sequencing, right? My document, my information, whatever it is I'm sending across the internet, is going to get cut into small little pieces. And we're going to see as we get down to layer 2, we're down to like 1,500 byte pieces. Not really very big. So these might, and they go on in a particular sequence, right? Segment 1, segment 2, segment 3. It may not arrive that way. It may get at my destination as segment 3, 2, 4, 1. Well, TCP puts a number on everything, so the receiving end can put it all in the correct order. It also does this thing called checksum, which is a little mathematical thing it does. Honestly, you want to know how it works? Take a class in really hard math. But it verifies that the data didn't get mangled in transport. So it wasn't distorted along the way. And it also does flow control, which is really putting an ear to the wire and finding out how quickly it can send stuff. Why would I want to use this? I would want to use TCP in those cases where I want to make sure that my data arrived, that I know it arrived, and that it got there in the right sequence and didn't get mangled. Oh, what would be good for this? Oh, online banking. That's a prime example of it. If I'm connected to my online bank and I'm making a $10 donation to the Save the Whales Fund, I don't want some data, a bit of data static, turning that into a $10,000 donation, right? I like whales, but not that much. If we actually look inside a TCP segment, this is what we're going to see. The data down here, this represents that first envelope that we receive from the application layer, right? So that information, that payload, that message was put into a segment, a TCP segment, and then all this other stuff right here is TCP header information. And it's got stuff like source and destination port. Well, we're going to talk more about ports later on, but port numbers do exist at layer 4. The sequence number, right? Which 1 out of 4, 1 out of 400, 1 out of 4,000, whatever. Things like the checksum value to make sure it didn't get mangled. Some padding in here to make sure the segment stays the same, a consistent size. And one thing that allows us to give us is that delivery confirmation. Well, I keep using this post office analogy, and it's pretty close. But what it really is a three-way handshake. And it's basically this, right? And this is for every segment that's being sent. Computer A sends a first segment over, right? Or basically goes to initiate the connection. Computer B answers it. Computer C says, okay, we're talking, we have a connection, so here comes a segment. And here comes a piece of data at you. And back and forth we go. This ensures me that all my data arrives there. If the receiving end is expecting a segment and doesn't get one, or the computer A sent a segment and doesn't get delivery confirmation, then it'll resend that missing segment. Now let's compare this to our other layer 4 protocol, UDP, User Datagram Protocol. This does nothing, or it does something. It sends segments, but it has no error checking, no sequencing, no delivery confirmation, no nothing. You send a segment down the wire and you hope it got there. It's kind of like going out to the beach with a bunch of bottles, writing a bunch of notes in them, throwing them into the ocean, and hoping that it arrives over in Portugal on the other side of the Atlantic from us. It might get there, might not. I don't know if it'll ever get there. That's what this does, right? So you're just sending a stream of data. And really, I just gave a great clue into when we would want UDP. We would use UDP in those cases that performance is an issue for us. So streaming video, streaming music, that type of thing. Online gaming, right? If I'm sitting there playing a first-person shooter, I don't want a missing segment replayed 4 seconds later. That's not going to do me any good. If I'm watching a YouTube video and I lose a segment, it gets mangled on the wire somewhere, worst that's going to happen is that my image will slightly pixelate and then it'll press on. Having a delivery confirmation, having it replayed, will not help me here. So when asked the question, which is better, TCP or UDP, the answer is yes. They're both useful. It all depends what your context is. What are you using it for? What's a better tool, a hammer or a screwdriver? All depends what you're doing. The UDP packet, or excuse me, the UDP segment is way simpler than the TCP one. Same idea, we still have this data, right? And yes, you see a checksum value here. It does do a checksum value just to see if it got mangled, but it's not to the extent that TCP does it. And then it's just two of the, really just source and destination port. Look how much more information was in TCP with this connection-orientated, reliable delivery method, right? Source port, sequence number, acknowledgement, all that kind of stuff. And under UDP, source, destination, checksum, and there's your data. So let's go down a little bit to layer 3 again. Let's look at our internet protocol, right? And we talked about this a bit, IPv4 versus IPv6. Well, internet protocols, either one of them, are not connection orientated. They don't do any type of delivery confirmation. They don't really do any kind of sequencing. So IP, the internet protocol at layer 3, relies on the protocols at layer 4 to guarantee delivery, or to not, right? But by itself, the internet protocol cannot do any of the things that TCP can do. Now, we've all seen these before. Let's look at the IPv4 address, right? And this is probably one of the most common ones you're ever going to see. IPv4 addresses are 32 bits in size, 32 binary bits, and we're going to spend a lot more time in later chapters going into that. Broken up into 4 octets. 1, 2, 3, 4. They're divided by periods here. Octet, oct, octagon, octopus, 8. 4 times 8, 32. That's where you get the 32 bits from. Well, the IP address identifies a node, and I'm going to use the term node instead of computer or server because our definition of what that can exist in our networks is very broad now. 25 years ago, not so much. You had computers on your network. But nowadays, we have smartphones, we have tablets, we have smart appliances. Over the last holiday break, my wife sent me a picture from Walmart of a crock pot that had Wi-Fi capability, and you would join it to your wireless network, and you could control it with your smartphone. Smart toasters, thermostats, all that kind of stuff. Those are all nodes on our network. If you're a node on a network, you require an IP address. Well, this IP address shows us two things. It tells us what network we are on and what my specific address for the host is. How does it do it? It does it with this thing right here called a subnet mask. Okay? Again, we're going to spend way more time on this in future chapters, but this is just to introduce you to it. The whole purpose of the subnet mask is to tell me what part of this IP address identifies the network and which part identifies the host. So in this case, this is a Class C, classful IP address. And this is a very common address. Just about every home router on the planet uses this addressing space right here. In classful addressing, and we're going to expand on this when we get to subnetting, but in classful addressing, an octet of my subnet mask that contains a 255 refers to the network. And an IP address by itself is useless. I have to have subnet mask information with it in order to know where my network is and where my host is. In this case, I have a 255 over the first octet, a 255 under the second octet, and a 255 under the third octet. So for this IP address, 192.168.1 represents my network number. Wherever there's a 0, that represents host. So .100 represents my host number. All of this taken together gives me my IP address. Well, data at layer 3 and IPv4, they're called packets. Remember, the name changes as we go through the stack. Up at the application layer, it's a payload or a message. At layer 4, it's a segment. At layer 3, it's a packet. And here's the same thing. Look inside here. Here's my data. And that is my entire TCP segment, or my entire UDP segment gets encapsulated inside an IP packet. Right? This is one envelope, and this is a bigger envelope, and I put this smaller one inside of it. But then on the front of this big envelope, I wrote a bunch of information. And look what we have going on here. We've got some information like time to live, how long should this packet exist, total length of it. There is a little checksum here for the header. But the big part of it is right here. Source IP address and destination IP address. What's the IP address of the machine that sent the packet, and what's the IP address of the machine that's going to receive the packet? This is why IP addresses are so important to us. Okay, let's take a quick leap right here. What happens below layer 3? Let's go back up real quick. Network interface layer. What's happening down here at the network interface layer? Layer 2 addresses, MAC addresses, media access control addresses. Right? The purpose of IP addresses is to identify the network. The purpose of the MAC address is to identify the node. So our packet then gets sent down to layer 2, where it becomes what's known as a frame. Right? How do we go back and forth between these two? How does layer 3 know how to talk to layer 2? Where does that translation happen? It does it with a protocol called ARP, Address Resolution Protocol. So let's say I have machine A talking to machine B. It's going to use a combination of subnet mask and IP address to figure out if machine B is on the same network as machine A. Remember that the subnet mask tells me what part of that IP address is network and which part is host? If it's not on the same network, then machine A sends that packet to a router. Right? It's called the default gateway usually, and the router is what figures out where that network is. If machine A realizes, hey, this machine B is on my same network, because it compared the IP addresses against NetMask, and it says, okay, you're on my local network segment. It now needs to go to layer 2 and talk at the MAC address level, down there at the physical level. Well, how does it do it? Address resolution protocol. And what happens is machine A will do what's called an ARP broadcast. What is a broadcast? A broadcast is when I talk to everybody on the network segment. And it'll blast it across that local network segment. Hey, who has the MAC address for IP address 192.168.1.100? All the machines in that subnet will hear it. So most machines say, nope, not me, and ignore it. Machine B, though, will say, hey, 192.168.1.100? That's me. It'll respond and say, I'm 192.168.1.100, and my MAC address is blah, blah, blah. At that point, machine A and machine B are communicating via MAC address. Right down here. Well, these hosts, machine A and machine B, will keep a record of it. We don't want to have to do ARP broadcasts for every single transmission. So all of our nodes maintain what we call ARP tables. And it's just a little list that maps an IP address, a layer 3 address, to a layer 2 MAC address. And it'll cache this. It means it'll hold it in memory for a period of time. So any future communication over the next few seconds, if you will, between machine A and machine B, they don't have to do an ARP broadcast again. Right? They've already got it. They've got that information. After the ARP table or the ARP entry expires, because they do have a lifespan on them, the machines will have to redo their ARP broadcast again and repopulate this table. Now, two kind of entries. We saw them in here before. Static and dynamic. Dynamic ones are created from ARP broadcast. It's possible to put a static entry in there, right? I might have a situation where my IP address will never change. And my MAC address should never change. I mean, it's a physical address burned into the chip on the network interface card. If I know that IP will never change, I could configure my node with a static one, right? A static ARP table entry. That means as long as it has this information, it'll never do an ARP broadcast to resolve those particular addresses. Thing is, layer 3 addresses, IP addresses, they're logical and they're very commonly dynamic, which means they change a lot. So if I have a changing IP address, I really don't want to have a static MAC address in there. You can look at your ARP table, totally. As a matter of fact, let's do that. I'm going to open a command window right here. You can see my Windows 10 terminal here, and it has a little bit of see-through effect, but you should be able to see it. And if I issue the ARP-A command, this will go through and display my laptop's ARP table entry. Right? And here are all different IP addresses that my laptop spoke to here in the recent past, and the corresponding MAC addresses. Yeah, kind of along those lines right here. And the table is dynamic, for dynamic entries. So it's going to change quite a bit. And with that, in the interest of keeping our lectures bite-sized, we're going to stop. And then when we come back in part 2, let's examine some network equipment. Let's take a close look at this thing we called a router. Might be a big deal. See you in a few.